Physics is the silent architect of the universe. The invisible framework governs planets' motion, stars' formation, and galaxies' evolution. It shapes how light travels billions of years and determines the forces holding the cosmos together. Every celestial body, from the smallest asteroid to the largest galaxy cluster, moves to the rhythm of these universal laws. As you relax, let us take a serene journey through the physics of space. Together we will explore the forces that sculpt the cosmos, the strange and beautiful phenomena that defy our intuition, and the profound truths that connect us to the universe. This is a journey into the fundamental principles of reality, a journey to the very heart of existence. The immensity of the cosmos. The scale of the universe is almost impossible to comprehend. The observable universe spans 93 billion light-years in diameter and contains over 200 billion galaxies. Each galaxy holds billions, sometimes trillions, of stars, many with their planetary systems. Yet, for all its immensity, we can see only a fraction of the whole. Did you know that visible matter, everything we can observe with telescopes and instruments, accounts for just 5% of the cosmos? The rest is composed of mysterious dark matter and dark energy, invisible forces that govern the structure and expansion of the universe. Space's immensity is matched only by its complexity. Every star, planet, and distant nebula is part of an intricate cosmic ballet, moving according to the fundamental laws of physics. These universal laws operate with the same precision whether we observe the planet's orbits or the dance of subatomic particles. The language of the universe. Physics is often described as the language of the universe. It allows us to translate the mysteries of space into equations, principles, and patterns we can understand. Gravity, electromagnetism, and quantum mechanics are the tools through which we interpret the cosmos, unveiling the beauty hidden in its workings. Gravity, the force that binds galaxies and curves the space-time fabric. Gravity gives the universe its structure, shaping the paths of stars and planets. Did you know that gravity is so subtle that it weakens with distance, yet so powerful that it can bend light? This bending is called gravitational lensing, allowing us to see objects billions of light-years away. Light, the messenger of the universe, traveling vast distances to bring us glimpses of the past. Light moves at 1.86000 miles per second, fast enough to circle Earth 7 times in 1 second. Every beam of light carries information about its source, its temperature, composition, and distance. By studying light, we unlock the stories of stars, galaxies, and the universe's origin. Quantum mechanics, the physics of the very small, where particles behave in ways that defy intuition. At the quantum level, particles can exist in multiple states simultaneously, a superposition phenomenon. Did you know that quantum physics underpins technologies like lasers, semiconductors, and the devices that allow us to explore space? Physics connects us to the cosmos by revealing its underlying simplicity. Despite the universe's vastness, Its behavior is governed by just a handful of fundamental laws and principles that can be written on a single page, yet describe the motion of galaxies and the energy of atoms. The time machine of the night sky. The night sky is more than just a collection of stars. It is a time machine. Every point of light you see has traveled across space for millions or even billions of years to reach your eyes. Looking at the stars, you look into the past, glimpsing moments frozen in time. Did you know that the light from some stars began its journey before Earth was even formed? The nearest star to our solar system, Proxima Centauri, is 4.24 light-years away, meaning its light takes over 4 years to reach us. But other stars are far more distant. Some of the faintest galaxies ever observed emitted their light over 13 billion years ago, when the universe was still in its infancy. Through physics, we can decode the messages carried by this ancient light. Its color, brightness, and wavelength shifts reveal the movement of galaxies, the composition of stars, and the rate at which the universe is expanding. By studying the light of the cosmos, we uncover the story of its evolution, from the fiery birth of stars to the vast structures we see today. The physics of space, a reflection of ourselves. Physics is not just a tool for understanding the cosmos. It is a reflection of ourselves. The same laws that govern the motion of galaxies also govern the atoms in our bodies. The same processes that power the stars also power the chemical reactions that sustain life on Earth. Did you know that the carbon in your body, the iron in your blood, were all forged in the cores of ancient stars? These elements were scattered into space when the stars died in spectacular explosions, seeding the universe with the building blocks of life. We are made of stardust. As we explore the physics of space, we are also exploring our origins. Every discovery we make, the nature of black holes, the behavior of quantum particles, or the structure of the cosmos, deepens our connection to the universe and reminds us of our place within it. An invitation to wonder. As we embark on this journey through the physics of space, let us be in awe and curiosity. The universe is vast and mysterious, governed by principles that are as elegant as they are powerful. Each space-time force, particle, and ripple tells a story that we are only beginning to understand. The physics of space is a reminder that the cosmos is both vast and intimate, a place where questions and answers intertwine. Tonight, as you listen, may these stories inspire peace, wonder, and a connection to the infinite. Gravity, the force that shapes the cosmos. Gravity is the silent architect of the universe. It is the force that binds galaxies, shapes stars, and shapes the orbits of planets. Without gravity, the cosmos as we know it would not exist. This fundamental force orchestrates every celestial motion, from Earth's steady spin to galaxies' spiraling collision. Yet gravity is more than just a physical force. It is a storyteller. It carries the universe's history, tracing its evolution from the earliest moments after the Big Bang to the present day. Through gravity, we understand how matter clumps together to form galaxies, how stars are born in stellar nurseries, and how black holes distort the very fabric of space-time. What is gravity? In its simplest form, gravity is the force of attraction between objects with mass. Sir Isaac Newton first described this force in the 17th century, defining it as a universal force that pulls objects toward one another. He gave us the elegant equation F equals G m1 m2/r2, where F is the gravitational force, m1 and m2 are the masses of two objects, r is the distance between them, and g is the gravitational constant. Newton's law explained everything from an apple's falling to planets' motion around the sun. However, as profound as Newton's work was, it left one question unanswered. Why does gravity exist? Einstein's revolution. Gravity as the curvature of space-time. In the early 20th century, Albert Einstein reimagined gravity in his theory of general relativity. According to Einstein, gravity is not a force in the traditional sense, but a consequence of the curvature of space-time. Imagine space-time as a flexible fabric. When a massive object like the Sun is placed on this fabric, it creates a dip or curve. Smaller objects, like planets, follow these curves, moving in orbits not because they are pulled by a force, but because they are traveling along the paths dictated by the shape of space-time. Did you know that Einstein's theory also predicts that time flows more slowly in stronger gravitational fields? This phenomenon, known as gravitational time dilation, has been confirmed through experiments and plays a critical role in technologies like GPS, which must account for the difference in time between satellites and Earth's surface. The role of gravity in shaping the universe. Gravity is the driving force behind the formation and evolution of cosmic structures, the birth of galaxies. In the early universe, matter was distributed almost uniformly. Small fluctuations in density, amplified by gravity, allowed matter to clump together, forming the first stars and galaxies. Over billions of years, gravity continued to shape these structures, pulling galaxies into clusters and connecting them through vast filaments of dark matter, creating the cosmic web we see today. Star formation. Gravity causes gas and dust to collapse within giant molecular clouds, forming dense cores that ignite nuclear fusion and give birth to stars. Did you know that gravity regulates the size of stars? If a collapsing cloud is too massive, it can fragment into smaller clouds, forming multiple stars instead of one giant star. Planetary systems? Gravity sculpts the disks of gas and dust around young stars, guiding the formation of planets, moons, and asteroids. These protoplanetary disks are the birthplaces of worlds like our own. Gravitational waves, ripples in space-time. One of the most astonishing predictions of Einstein's theory of general relativity is the existence of gravitational waves. Ripples in the fabric of space-time caused by the acceleration of massive objects. How gravitational waves are created. Cataclysmic events such as the collision of black holes, the merging of neutron stars, or the explosion of massive stars in supernovae produce gravitational waves. These waves travel across the universe at the speed of light, carrying information about their origins and the objects that created them. Detecting gravitational waves in 2015, scientists at LIGO, Laser Interferometer Gravitational Wave Observatory, made the first direct detection of gravitational waves, confirming Einstein's prediction a century earlier. The ripples detected were from two black holes merging over 1 billion light-years away, a discovery that opened a new window into the universe. Did you know that detecting gravitational waves requires measuring distortions in space smaller than the width of a proton? This incredible precision demonstrates the ingenuity of modern science. Gravity and the concept of escape velocity. Gravity holds objects close to celestial bodies, but an object can break free with enough speed. The escape velocity is the minimum speed depending on the body's mass and the distance from its center. Escape velocity on Earth. To escape Earth's gravity, an object must reach a speed of 11.2 kilometers per second, about 2,5,0,0,0 miles per hour. Rockets achieve this by carrying fuel for continuous thrust, overcoming gravity's pull. Black holes and event horizons. In black holes, the escape velocity exceeds the speed of light, creating a region where nothing, not even light, can escape. This boundary is called the event horizon. Gravity's influence on time and space. Gravity doesn't just affect motion, it also warps time and space. Gravitational time dilation. Time flows more slowly in stronger gravitational fields. Near a black hole, time could stretch so much that a few hours for an astronaut might equal years for an observer far away. Did you know GPS satellites experience gravitational time dilation because they are farther from Earth's gravity? Scientists must adjust their clocks to ensure accurate positioning. The curvature of space, gravity warps space, bending the paths of light and matter. This effect is most noticeable near massive objects like black holes, where light follows curved paths. Gravity, the force that connects us. Gravity is more than a physical force. It is a cosmic thread that connects everything in the universe. It binds galaxies, guides the motion of planets, and creates the conditions for life to exist. Without gravity, there would be no stars, planets, or us. As we reflect on gravity's role in shaping the cosmos, we are reminded of our place within this grand design. The same force that governs the motion of galaxies also governs the tides on Earth and the beating of our hearts. Gravity is a unifying force, a constant presence in an ever-changing universe. Light and electromagnetic waves, the messengers of the universe. Light is the universe's messenger, carrying information across unfathomable distances and revealing the secrets of the cosmos. It allows us to see the stars, measure the movements of galaxies, and study phenomena billions of light-years away. Yet, light is more than just a tool for observation. It is a cornerstone of physics, a bridge between the visible and invisible, and a key to understanding the universe's very nature. The nature of light. A wave and a particle. Light is one of the most fascinating phenomena in physics. It behaves as a wave and a particle, the concept known as wave-particle duality. Light as a wave. Light is an electromagnetic wave of oscillating electric and magnetic fields propagating through space. Its wavelength determines its color and type, from the longer wavelengths of infrared to the shorter wavelengths of ultraviolet. Did you know that the visible spectrum, the light we can see, represents only a tiny portion of the electromagnetic spectrum? Light as a particle. Light also behaves as a particle, carrying energy in discrete packets called photons. Photons have no mass but possess energy, allowing them to interact with matter in ways that produce everything from the warmth of sunlight to the glow of distant stars. This duality lies at the heart of quantum mechanics, revealing light's unique ability to bridge the world of waves and particles. The electromagnetic spectrum, the universe's hidden light. The electromagnetic spectrum is a continuum of all types of electromagnetic radiation, ranging from low-energy radio waves to high-energy gamma rays. Each part of the spectrum reveals a different aspect of the universe. Radio waves. Radio waves, the longest wavelengths in the spectrum, are used to study some of the universe's most mysterious phenomena, such as pulsars, quasars, and cosmic microwave background radiation. Did you know that radio telescopes like the iconic Arecibo Observatory have detected signals from objects billions of light-years away? Microwaves. Microwaves are used to study the remnants of the Big Bang, known as the cosmic microwave background, CMB. The CMB is a faint glow of radiation that permeates the universe, providing a snapshot of its earliest moments. Infrared light. Infrared light reveals the heat emitted by objects, allowing us to study star-forming regions, distant planets, and even the structure of galaxies obscured by dust. Infrared telescopes like the James Webb Space Telescope can peer through cosmic dust clouds, unveiling hidden wonders. Visible light. This narrow spectrum band is the light we can see with our eyes. It allows us to observe stars, planets, and galaxies directly. Did you know that the sun emits most of its energy in the visible spectrum, making it ideally suited for life on Earth? Ultraviolet light, hot. Young stars produce ultraviolet radiation and can reveal details about star formation and the dynamics of galaxies. It also plays a critical role in understanding the atmospheres of exoplanets. X-rays allow us to study high-energy phenomena like black holes, neutron stars, and supernova remnants. Did you know that NASA's Chandra X-ray Observatory has captured some of the most detailed images of black hole activity? Gamma rays. The most energetic form of electromagnetic radiation, gamma rays are produced by the universe's most extreme events, including gamma ray bursts and matter falling into black holes. Gamma ray telescopes, like the Fermi Gamma Ray Space Telescope, detect these bursts of energy and provide insights into the cosmos's most violent processes. Each wavelength of light is like a different language the universe uses to communicate. Studying the entire spectrum gives us a more complete picture of the cosmos. The speed of light. The cosmic speed limit. Light travels at an astonishing speed of 2,99792 kilometers per second, about 186,000 miles per second. making it the fastest thing in the universe. This speed, however, is not infinite. It sets a fundamental limit on how quickly information and energy can travel. The concept of light years, a light year is the distance light travels in 1 year, about 9.46 trillion kilometers, 5.88 trillion miles. Did you know that when we observe distant galaxies, we see them as they were millions or even billions of years ago? The light we observe began its journey long before life on Earth existed. Relativity and the speed of light. According to Einstein's theory of special relativity, the speed of light is constant for all observers, regardless of their motion. This constancy has profound implications for space and time, leading to phenomena like time dilation and length contraction. The speed of light connects space and time, forming the foundation of modern physics. It is both a bridge to the past and a guide to the future, revealing the universe's story, one photon at a time. Light as a messenger, decoding the universe's secrets. Light carries with it a wealth of information about its source. By analyzing light, scientists can uncover the secrets of stars, galaxies, and the universe's origins. Spectroscopy is the study of how light interacts with matter. By splitting light into its component colors, scientists can determine celestial objects' composition, temperature, and motion. Did you know that the dark lines in a star's spectrum, called absorption lines, act like fingerprints, revealing the elements present in its atmosphere? Redshift and blueshift, light from objects moving away from us, is stretched, appearing redder, a phenomenon known as redshift. Objects moving toward us exhibit blueshift, where light is compressed. Redshift is a key piece of evidence for the universe's expansion and has been used to measure the distance to galaxies billions of light-years away. Polarization. Light waves can vibrate in specific directions, a property known as polarization. By studying polarized light, scientists gain insights into the alignment of magnetic fields and light scattering in cosmic dust clouds. Light, a connection to the cosmos. Light is more than just a physical phenomenon. It is a connection to the cosmos. It bridges the vast distances of space, linking us to stars, galaxies, and the universe's history. Every photon carries a message, a story of creation, destruction, and transformation. Did you know that the starlight you see tonight began its journey long before humanity existed? Each point of light in the sky reminds us how deeply we are connected to the universe. A universe where light serves as both a guide and a messenger, illuminating the mysteries of existence. Space-time, the fabric of reality. Space and time are not separate entities. They are deeply intertwined, forming a single fabric known as space-time. This concept, introduced by Albert Einstein in his theory of general relativity, revolutionized our understanding of the universe. Space-time is not a passive backdrop. It is dynamic, bending, and stretching in response to mass and energy. Everything in the universe, from the motion of planets to the expansion of galaxies, is governed by the geometry of space-time. Yet space-time is not just a scientific abstraction. It is the stage upon which the drama of the cosmos unfolds, shaping the very nature of reality itself. The nature of space-time. Space-time is a four-dimensional continuum that combines the three dimensions of space, length, width, and height, with the dimension of time. Together, these dimensions form the framework of the universe and determine how objects move and interact. Space-time as a dynamic fabric. Massive objects, like stars and planets, warp the fabric of space-time, creating curves that other objects follow. This curvature is what we perceive as gravity. For example, Earth orbits the Sun not because it is pulled by a force, but because it follows the curved path created by the Sun's mass. The inseparability of space and time is not independent of space. They are fundamentally linked. An event's location in the universe is defined by its position in space and its moment in time. Did you know that even the passage of time is affected by the curvature of spacetime? This is why time flows differently depending on the strength of gravity and the relative speed of an observer. Einstein's revolution, general relativity. Albert Einstein's theory of general relativity published in 1915, reshaped our understanding of gravity and introduced the concept of space-time as a dynamic entity. Gravity, as the curvature of space-time, general relativity, showed that gravity is not a force in the traditional sense, but the result of massive objects bending the fabric of space-time. The greater the mass, the more pronounced the curvature. For example, the sun's mass creates a deep well in space-time which governs the orbits of planets. The warping of time flows more slowly in stronger gravitational fields, a phenomenon known as gravitational time dilation. Near massive objects like black holes, time stretches to extremes. Did you know that astronauts on the International Space Station experience time slightly faster than people on Earth due to the weaker gravity in orbit and reduced to a minimum stationary point? This difference, though tiny, has been measured with incredible precision. Tests of general relativity has been confirmed through numerous experiments, from the bending of starlight during solar eclipses to the detection of gravitational waves. One of its most dramatic predictions is the existence of black holes, regions where space-time curves so steeply that not even light can escape. Time dilation, the elasticity of time. Time is not absolute. It is relative, stretching and compressing depending on gravity and velocity. Gravitational time dilation. In regions of strong gravity, time slows down. This effect has been observed in experiments where clocks placed at different altitudes, closer and farther from Earth's gravity, tick at slightly different rates. Near a black hole, time dilation becomes extreme. A few hours near the event horizon could equal years or even centuries for an observer far away. Time dilation and velocity. Time also slows down for objects moving at high speeds, an effect predicted by Einstein's theory of special relativity. Did you know that astronauts on high-speed missions, like those aboard the ISS, experience time dilation? Over long periods, they age slightly slower than people on Earth. Practical implications. Time dilation is not just a theoretical curiosity. It has practical applications. Speed is real. GPS satellites, for example, must account for both gravitational and velocity-based time dilation to provide accurate positioning. Black holes, space-time's extreme distortion. Black holes are the most extreme examples of warped space-time, where gravity becomes so intense that it creates regions of no return. The event horizon. The event horizon is the boundary of a black hole beyond which nothing, not even light, can escape. It marks the edge of space-time's most dramatic curvature. Did you know that the event horizon is not a physical surface but a mathematical boundary? Objects crossing it are forever lost to the black hole's gravity. Singularity, the heart of a black hole. At the center of a black hole lies the singularity, a point of infinite density where space-time curves infinitely. The singularity represents a breakdown of our current understanding of physics, suggesting the need for a unified theory of general relativity and quantum mechanics. Black holes as cosmic laboratories. Black holes provide unique opportunities to study the nature of space-time. Observing their behavior offers insights into gravity, quantum mechanics, and the structure of the universe. The expanding universe, space-time on a cosmic scale. Space-time is not static. It is dynamic, stretching and expanding as the universe evolves. The Big Bang and the birth of space-time. The universe began approximately 13.8 billion years ago in a hot, dense state known as the Big Bang. Space-time itself was born in this moment, expanding rapidly in the first fractions of a second. This expansion continues today, driving galaxies farther apart and increasing the scale of the universe. The role of dark energy. Dark energy, a mysterious force, accelerates the expansion of space-time. It constitutes about 68% of the universe, yet its nature remains one of the greatest mysteries in physics. Did you know that as space-time expands, the distances between galaxies increase, but the galaxies themselves do not expand? The fate of the universe, the ultimate fate of space-time, depends on the balance between dark energy, gravity, and the universe's overall density. Will it expand forever, collapse in a big crunch, or fade into a cold, dark void. Space-time, the stage of the universe. Space-time is more than a scientific concept. It is the framework of existence. It determines how objects move, time flows, and the universe evolves. Everything is shaped by the geometry of space-time, from the smallest particles to the largest galaxies. When we consider the nature of space-time, we are reminded of its profound beauty and complexity. It is not just the stage of the universe, it is the fabric that binds it together, weaving the stories of stars, planets, and life itself. The quantum world, the physics of the very small. Beneath the visible universe lies a hidden realm, the quantum world, a place where the laws of physics as we know them begin to break down. This is a domain of probabilities, paradoxes, and phenomena so strange that they defy common sense. Here, particles behave like waves, objects exist in multiple states at once, and the act of observation itself influences reality. The quantum world is the foundation of everything. It governs the behavior of the smallest building blocks of matter, particles like electrons, photons, and quarks. It is also the birthplace of many of the universe's most profound mysteries, from the nature of dark matter to the origins of space-time itself. What is quantum mechanics? Quantum mechanics is the branch of physics that describes the behavior of matter and energy at the most minor scales. At this level, the familiar rules of classical physics no longer apply. Instead, reality is governed by principles that are often counterintuitive but profoundly elegant. Wave-particle duality, the idea that particles like electrons and photons can behave as both particles and waves. For example, light, which was once thought to be purely a wave, also exhibits particle-like behavior. This duality is seen in phenomena like the double-slit experiment, where particles create an interference pattern when unobserved, but act like particles when measured. Superposition. In the quantum world, particles can exist in multiple states simultaneously. This phenomenon, known as superposition, allows particles to be in two places at once, or have multiple properties until they are observed. Did you know that this principle underpins technologies like quantum computing, where particles in superposition can perform many calculations at the same time? The uncertainty principle, as proposed by Werner Heisenberg, the uncertainty principle states that the specific properties of particles, such as their position and momentum, cannot be measured with absolute precision. The more accurately one property is known, the less accurately the other can be determined. This principle reflects the fundamental probabilistic nature of the quantum world. Quantum entanglement, spooky action at a distance. The most perplexing phenomenon in quantum mechanics is quantum entanglement, a connection between particles that persists regardless of the distance between them. What is entanglement? When two particles become entangled, their properties are linked in such a way that measuring one instantly determines the state of the other, even if they are light years apart. This defies classical physics, where information cannot travel faster than the speed of light. Einstein's skepticism, Albert Einstein famously referred to entanglement as spooky action at a distance, questioning how such a phenomenon could occur. However, experiments have repeatedly confirmed its reality. Did you know that quantum entanglement is now being used to develop ultra-secure communication systems and quantum networks? Implications for reality. Entanglement challenges our understanding of causality and locality, suggesting that the universe may be fundamentally interconnected in ways we do not yet fully understand. Quantum fluctuations, the seeds of the universe. The quantum world is not static. It is filled with activity, even in seemingly empty space. This activity is driven by quantum fluctuations, temporary changes in energy that occur spontaneously at the most minor scales. What are quantum fluctuations? In the quantum vacuum, particles and antiparticles briefly pop into existence before annihilating each other. These fluctuations are a natural consequence of the uncertainty principle. Did you know that these fleeting events can have real, observable effects, such as the Casimir effect, where quantum fluctuations create an attractive force between two closely placed surfaces? Cosmic implications. In the early universe, quantum fluctuations played a critical role in shaping the cosmos. During the period of cosmic inflation, these tiny fluctuations were stretched to cosmic scales, creating the seeds for galaxies and large-scale structures. Without quantum fluctuations, the universe would be a uniform, featureless expanse. No stars, no galaxies, no life. The quantum field. The fabric of reality. At the heart of quantum mechanics lies the concept of the quantum field, an invisible framework that fills all of space. What is a quantum field? Every particle in the universe is associated with a quantum field. For example, electrons arise from the electron field, and photons emerge from the electromagnetic field. Particles are not independent entities, but rather excitations or ripples in their respective fields. The Higgs field. The discovery of the Higgs boson in 2012 confirmed the existence of the Higgs field, which gives particles their mass. Did you know that without the Higgs field, particles like electrons would be massless, and the universe would lack the structure needed for stars, planets, and life? Virtual particles, quantum fields, also give rise to virtual particles, which existed briefly before vanishing. These particles mediate forces like electromagnetism and the strong nuclear force. The role of quantum mechanics in modern physics. Quantum mechanics is not just a theoretical framework. It is the foundation of modern physics and technology. Applications in technology. Quantum mechanics underpins many of the technologies we use daily, including transistors, lasers, and MRI machines. Quantum computing, a rapidly advancing field, promises to revolutionize computation by leveraging the principles of superposition and entanglement. The search for quantum gravity. One of the most significant challenges in physics is reconciling quantum mechanics with general relativity. The quest for a unified theory, such as string theory or loop quantum gravity, seeks to describe the behavior of space-time at the most minor scales. Quantum mechanics and the cosmos. Quantum mechanics plays a key role in understanding the universe's most extreme environments. From the interiors of black holes to the conditions of the Big Bang. The quantum world, a realm of infinite possibilities. The quantum world is a place of infinite possibilities, where particles can exist in multiple states and reality is shaped by probabilities. It is a realm that challenges our intuition but reveals the profound interconnectedness of the universe. Did you know that everything around you, from the atoms in your body to the light from the stars, is governed by quantum mechanics? The quantum world is not separate from our reality. It is the foundation of it. Thermodynamics in space, the flow of energy across the cosmos. Thermodynamics is the study of energy, how it flows, transforms, and shapes the universe. It governs the behavior of everything from the smallest particles to the most significant cosmic structures. In the vacuum of space, where temperatures range from the searing heat near stars to the frigid cold of interstellar voids, the laws of thermodynamics dictate how energy moves and how the universe evolves over time. At its core, thermodynamics is the fundamental balance between order and entropy, creation and decay. It is the unseen mechanism that powers the cosmos, influencing the life cycles of stars, the formation of planets, and even the ultimate fate of the universe itself. What is thermodynamics? Thermodynamics is the branch of physics that deals with heat, energy, and work. It is governed by 4 fundamental laws that describe how energy behaves in isolated systems, laws that are as relevant to the workings of the universe as they are to the boiling of water on Earth. The first law, conservation of energy. Energy cannot be created or destroyed. It can only change form. This principle, also known as the law of energy conservation, ensures that the total amount of energy in a closed system remains constant. Did you know that the energy radiated by a star like the Sun is the result of nuclear fusion, where hydrogen is converted into helium? The energy released is not lost, but radiates outward as light and heat. The second law, entropy always increases. The second law states that the total entropy, or disorder, of an isolated system always increases over time. This law introduces the concept of the arrow of time, which gives the universe its directionality. Did you know that the reason a hot object cools down but never spontaneously heats up is due to the second law? Energy flows from areas of higher concentration to lower concentration, creating balance but increasing entropy. The third law, absolute zero, is unattainable. As a system approaches absolute zero, the lowest possible temperature, where all molecular motion ceases, its entropy approaches a minimum. However, reaching absolute zero is physically impossible. In the coldest regions of space, temperatures come close to absolute zero, but quantum effects ensure that some energy always remains. Know the zeroth law, thermal equilibrium. If two systems are in thermal equilibrium with a third, they are in equilibrium with each other. This law establishes the concept of temperature and forms the basis for thermometers. The flow of energy in space. Energy flows constantly throughout the universe, shaping its structures and driving its processes. From the nuclear reactions in stars to the cooling of interstellar gas, thermodynamics governs the movement and transformation of energy. Stars as engines of thermodynamic, stars are the most visible examples of thermodynamic processes in action. Through nuclear fusion, they convert hydrogen into helium, releasing immense amounts of energy as light and heat. The energy produced by a star balances the inward pull of gravity, creating a stable system. This balance continues until the star exhausts its fuel, at which point thermodynamic processes determine its fate. Heat transfer in space? In the vacuum of space, heat transfer occurs primarily through radiation. Unlike conduction or convection, which require matter, radiation allows energy to travel through the void as electromagnetic waves. Did you know that the heat from the sun takes about 8 minutes to reach Earth, traveling across the vacuum of space as light? Cosmic cooling. As the universe expands, it cools. The cosmic microwave background radiation, the faint glow left over from the Big Bang, is a testament to this cooling process. Initially as hot as the core of a star, the universe has cooled to just 2.7 Kelvin, minus 270.45 degrees Celsius, barely above absolute zero. Entropy. The air of time. Entropy is a measure of disorder in a system, and it is constantly increasing in the universe. This principle defines the arrow of time, giving direction to processes that are otherwise reversible. The role of entropy in stars. Inside stars, entropy increases as hydrogen is fused into helium. Over time, this process produces heavier elements, eventually leading to the star's death. Did you know that the elements in your body, such as carbon and oxygen, were created in stars as they increase their entropy? The heat death of the universe. If the universe continues to expand indefinitely, it will reach a state of maximum entropy where all energy is evenly distributed and no work can be done. This scenario is known as the heat death of the universe. In this distant future, stars will have burned out, black holes will have evaporated, and the cosmos will become a cold, dark expanse. Thermodynamics and black holes. Black holes are fascinating laboratories for studying thermodynamics, where extreme conditions push the laws of physics to their limits. Black hole thermodynamics. Black holes have entropy proportional to the area of their event horizon. This discovery, made by Stephen Hawking and Jacob Bekenstein, revealed a surprising connection between thermodynamics and gravity. Did you know that black holes also radiate energy in the form of Hawking radiation, slowly losing mass over time? The information paradox. When matter falls into a black hole, its information seems to disappear, violating the laws of thermodynamics. This paradox has puzzled physicists for decades and remains an active area of research. The fate of black holes. Over billions of years, Hawking radiation causes black holes to shrink and eventually evaporate. The energy released during this process adds to the universe's entropy, further increasing its disorder. Thermodynamics in the formation of planets and galaxies. Thermodynamics plays a critical role in the formation of planets, stars, and galaxies. Planetary formation. As gas and dust collide within protoplanetary disks, heat is generated, causing the materials to clump together. Over time, these clumps grow into planets. Did you know that the heat generated during a planet's formation can remain trapped for billions of years? This is why Earth's core is still molten. Galactic evolution, galaxies. In galaxies, thermodynamic processes drive the formation of stars and regulate the distribution of gas and energy. Supernovae, for example, release massive amounts of heat and energy, triggering star formation in surrounding regions. The eternal flow of energy. Thermodynamics is the engine of the universe, guiding the flow of energy from stars to galaxies, from the Big Bang to the distant future. It reminds us that the cosmos is not static, but constantly evolving, shaped by the interplay of heat, entropy, and time. Did you know that even in the coldest, darkest corners of space, energy is still present? The faint glow of the cosmic microwave background is a reminder that the universe's story is one of motion, transformation, and endless possibilities. Motion in space, orbits, trajectories, and the cosmic ballet. The universe is in constant motion. From the smallest particles to the most significant galaxy clusters, nothing in space is truly at rest. Planets orbit stars, stars orbit galactic centers, and galaxies themselves drift through the expanding universe. This motion is not random. It is governed by the elegant principles of physics, creating a cosmic ballet that has played out for billions of years. The study of motion in space, rooted in the laws of Newton and Einstein, reveals the interconnectedness of the cosmos. It explains how celestial bodies move, how spacecraft navigate the void, and how gravity choreographs the intricate dance of the heavens. Newton's laws of motion. The foundation of celestial mechanics. In the 17th century, Isaac Newton laid the groundwork for our understanding of motion in space with his three laws of motion and the law of universal gravitation. These principles form the foundation of celestial mechanics, explaining how objects move in the absence of friction and air resistance. The first law, inertia. An object at rest will remain at rest, and an object in motion will continue in motion at a constant velocity unless acted upon by an external force. Did you know that a spacecraft in deep space, far from gravitational influences, could theoretically travel forever without slowing down? This is due to the absence of friction or air resistance in the vacuum of space. The second law, force and acceleration. The force acting on an object is equal to its mass multiplied by its acceleration, F equals ma. This law explains how celestial bodies respond to gravitational forces. For example, the acceleration of a planet toward the sun is determined by the sun's gravitational pull and the planet's mass. The third law, action and reaction. For every action, there is an equal and opposite reaction. This principle explains how rockets propel themselves through space by expelling gas in the opposite direction. The law of universal gravitation. Newton's law of universal gravitation states that every mass in the universe attracts every other mass with a force proportional to their masses and inversely proportional to the square of the distance between them. This law governs everything from the orbits of planets to the trajectories of comets. The elegance of orbits, the dance of planets and moons. Orbits are one of the most elegant manifestations of motion in space. They are the result of a delicate balance between two opposing forces, the gravitational pull of a massive object and the inertia of a moving body. Kepler's laws of planetary motion. In the early 17th century, Johannes Kepler refined our understanding of orbits with his three laws of planetary motion. First law, planets move in elliptical orbits with the sun at one focus. Second law, a planet sweeps out equal areas in equal times, meaning it moves faster when closer to the sun and slower when farther away. Third law, the square of a planet's orbital period is proportional to the cube of its average distance from the sun. Did you know that Earth's orbit is almost circular but not perfectly so? This slight eccentricity affects the intensity of seasons, tidal forces, and orbital resonance. Tidal forces, caused by the gravitational interaction between celestial bodies, play a significant role in shaping orbits. For example, the Moon's gravitational pull creates tides on Earth and is slowly causing the Moon to drift farther away. Orbital resonance, where two or more bodies exert periodic gravitational influences on each other, stabilizes certain orbits, such as those of Jupiter's moons Io, Europa, and Ganymede. Escape velocity. To leave an orbit or escape the gravitational pull of a planet, an object must reach a specific speed, known as the escape velocity. For Earth, this velocity is about 11.2 kilometers per second, 250,000 miles per hour. Trajectories in interstellar travel. Understanding motion is crucial for plotting trajectories and navigating the vast distances between planets and stars in space exploration. Hohmann transfer orbits. A Hohmann transfer orbit is the most energy-efficient way to move a spacecraft between two orbits. By timing the launch to align with the target's orbit, spacecraft can use minimal fuel to reach their destination. Did you know the journey to Mars typically takes 6 to 8 months using a Hohmann transfer orbit? Gravity assists. Spacecraft often use gravity assists or slingshots to gain speed and alter their trajectories. By passing close to a planet, they borrow some of its orbital energy, reducing fuel needs. For example, the Voyager probes used gravity assists from Jupiter and Saturn to accelerate toward the outer solar system. Interstellar travel. While current technology limits us to traveling within the solar system, concepts like ion propulsion and solar sails offer potential pathways for interstellar exploration. Did you know that the Parker Solar Probe, launched in 2018, uses a combination of gravity assists and solar energy to approach the Sun closer than any spacecraft in history? The motion of stars and galaxies. Motion is not confined to planets and spacecraft. It is a fundamental aspect of stars, galaxies, and the universe. Stellar motion. Stars within galaxies move in orbits around their galactic centers. For example, our Sun takes approximately 225 million years to complete one orbit around the center of the Milky Way. Did you know that stars also exhibit random motion due to gravitational interactions, forming clusters and streams? Galactic motion. Galaxies move within galaxy clusters, influenced by the combined gravity of dark matter and visible matter. Some galaxies, like the Andromeda Galaxy, are on collision courses with others. In about 4.5 billion years, the Milky Way and Andromeda will merge to form a single, larger galaxy. Cosmic expansion. On the largest scales, the universe is expanding, causing galaxies to move away. This motion is described by Hubble's law, which states that a galaxy's recessional velocity is proportional to its distance. The cosmic ballet. Harmony in motion. Motion in space is more than a series of mechanical processes. It is a cosmic ballet where every object follows a precise yet harmonious path. From the steady orbit of a planet to the chaotic dance of galaxy clusters, the universe is a testament to the elegance of physics. Did you know that the gravitational interactions shaping this dance will continue for billions of years after humanity is gone? The cosmic ballet is eternal, a reminder of the interconnectedness of all things. Dark matter and dark energy, the universe's hidden forces. The universe is a puzzle, and much of it remains hidden from our senses. Everything we see, the stars, planets, galaxies, and even ourselves, accounts for just 5% of the universe's total composition. The remaining 95% is made up of two enigmatic forces, dark matter and dark energy. Dark matter and dark energy are invisible to our eyes, yet their effects are profound. Dark matter acts as the universe's scaffolding, holding galaxies together and shaping the cosmic web. Dark energy, on the other hand, drives the accelerated expansion of the universe, pulling galaxies apart. Together, these mysterious components challenge our understanding of physics, raising profound questions about the nature of reality. What is dark matter? Dark matter is a form of matter that does not emit, absorb, or reflect light, making it invisible to telescopes. Despite its invisibility, dark matter exerts a powerful gravitational influence, shaping the structure and motion of the universe. Evidence for dark matter. The existence of dark matter was first proposed in the 1930s by Swiss astronomer Fritz Zwicky, who observed that galaxies in clusters were moving faster than expected based on their visible mass. Later, in the 1970s, astronomer Vera Rubin provided further evidence by studying the rotation curves of galaxies. She found that the outer regions of galaxies were rotating as fast as the inner regions, an observation that could only be explained by the presence of an unseen mass. The role of dark matter. Dark matter acts as the glue that holds galaxies and galaxy clusters together. Without it, galaxies would fly apart due to their rotational speeds. It also plays a critical role in the formation of cosmic structures, providing the gravitational scaffolding around which gas and dust can coalesce to form stars and galaxies. What could dark matter be? Scientists believe dark matter is made up of particles, but its exact nature remains unknown. Leading candidates include WIMPs, weakly interacting massive particles, hypothetical particles that interact only through gravity and the weak nuclear force, axions, ultralight particles that could solve several mysteries in particle physics, sterile neutrinos, a type of neutrino that does not interact with normal matter. Did you know that dark matter could pass through your body at this very moment without you noticing? It interacts so weakly with normal matter that it leaves no trace. What is dark energy? While dark matter holds the universe together, dark energy is a force that drives it apart. Discovered in the late 1990s, dark energy is the mysterious anti-gravity force responsible for the accelerated expansion of the universe. The discovery of dark energy was first inferred from observations of distant supernovae, which appeared dimmer than expected. This indicated that the universe's expansion was not slowing down as previously thought, but accelerating. Did you know that this discovery earned Saul Perlmutter, Brian Schmidt, and Adam Rees the 2011 Nobel Prize in Physics? The role of dark energy. Dark energy constitutes about 68% of the universe, making it the dominant component of cosmic energy density. It is believed to be uniformly distributed throughout space, exerting a repulsive force that counteracts gravity on the largest scales. The nature of dark energy. The exact nature of dark energy remains one of the greatest mysteries in physics. Possible explanations include the cosmological constant, a term in Einstein's equations representing a constant energy density inherent to space itself. Quintessence, a dynamic field that evolves over time rather than remaining constant. Modified gravity, the possibility that our understanding of gravity needs to be revised on cosmic scales. The cosmic web, dark matter's invisible structure. The cosmic web is the large-scale structure of the universe formed by the interplay of dark matter and gravity. The formation of the cosmic web in the early universe, small fluctuations in density were amplified by gravity, causing dark matter to clump together. These clumps became the seeds of galaxies and galaxy clusters connected by filaments of dark matter. Did you know that the cosmic web is sometimes called the skeleton of the universe? It provides the framework for the distribution of galaxies. The role of dark matter in the web. Dark matter makes up most of the mass in the cosmic web, guiding the motion of galaxies and the flow of gas. Observing the cosmic web allows scientists to study the distribution of dark matter even though it is invisible. Baryonic matter versus dark matter. Only about 15% of the universe's matter is baryonic, normal matter. The rest is dark matter, which forms the bulk of the cosmic web. Dark energy and the universe's fate. Dark energy is not just shaping the present, it will determine the ultimate fate of the universe. The Big Freeze. If dark energy remains constant or increases in strength, the universe will continue to expand forever. Over time, galaxies will drift farther apart, stars will burn out, and the universe will grow cold and dark, a scenario known as the Big Freeze, the Big Rip. If dark energy's strength increases dramatically, it could eventually tear apart galaxies, stars, planets, and even atoms. This hypothetical scenario is known as the Big Rip, the Big Crunch. If dark energy weakens or reverses, gravity could eventually halt the expansion of the universe, causing it to collapse back into a hot, dense state. A big crunch that could potentially lead to a new Big Bang, the mystery of the universe's hidden forces. Dark matter and dark energy remind us how much we still don't know about the universe. These hidden forces challenge our understanding of physics, inviting us to explore beyond the boundaries of what we can see and measure. Did you know that studying dark matter and energy is not just about understanding the universe, but our place within it? These mysteries are a testament to the infinite complexity of the cosmos, inspiring curiosity and wonder. Conclusion. Reflecting on the physics of space and the infinite mysteries of the cosmos. The universe is infinite in its beauty and complexity. It is both deeply familiar in the warmth of sunlight and the pull of gravity, and profoundly mysterious in the vast stretches of space and the forces we cannot see. Every law of physics, every particle, and every distant star tells a story, not just about the cosmos, but about us, humanity, and our quest to understand the world around us. As we conclude this journey through the physics of space, it is time to reflect on what we have learned, what remains unknown, and what this tremendous cosmic tapestry means for our place. The universe's grand symphony, revisiting the themes of the journey. Over the past 3 hours, we've delved into the physics of space, uncovering the forces and principles that govern the universe. Let's revisit the journey and reflect on the profound truths we've encountered. Gravity, the universal sculptor. Gravity is the architect of the cosmos, shaping the orbits of planets, the structure of galaxies, and the delicate balance of the universe. The endless earth and heaven hold their altar. It binds stars into galaxies, pulls matter together to form planets, and warps space-time itself around massive objects. Did you know that without gravity, the universe as we know it could not exist? Stars would not form, galaxies would disperse, and life would be impossible. Light, the universe's messenger. Light is the thread that connects us to the distant past. It carries the stories of stars that lived and died billions of years ago, and reveals the secrets of galaxies at the edge of the observable universe. From the warmth of sunlight to the faint glow of the cosmic microwave background, light is the language through which the cosmos speaks to us. Space-time. The fabric of reality, space and time are not separate entities, but a unified fabric that bends, stretches, and evolves. Einstein's theory of general relativity showed us that massive objects like black holes can warp space-time, creating gravitational wells that trap light and matter. Did you know that time flows differently depending on gravity? Near a black hole, time slows dramatically compared to regions of weaker gravitational influence. Quantum mechanics, the realm of the very small. At the most minor scales, the universe behaves in ways that defy intuition. Particles exist in superpositions, entangle across vast distances, and fluctuate in and out of existence. The quantum realm is the foundation of all matter, revealing a probabilistic, interconnected, and endlessly surprising reality. Energy. Giving the universe its irreversible arrow of time. Giving the universe its irreversible arrow of time. Do you know that the ultimate fate of the universe is its irreversible arrow of time? Did you know that the ultimate fate of the universe depends on energy? Whether it ends in a heat death, a big rift, or a cosmic rebirth, energy will decide the cosmos's final chapter. The motion of the cosmos, planetary orbits, spacecraft trajectories, and galaxies' movements are all part of a grand cosmic dance governed by precise laws that balance gravity, inertia, and energy. Even galaxies move within the cosmic web, influenced by the unseen forces of dark matter and the expanding fabric of space-time. The hidden universe, dark matter and dark energy. Most of the universe remains invisible, dominated by dark matter and energy. These mysterious components shape the structure and destiny of the cosmos, yet their true nature remains elusive. Did you know that dark matter acts as the scaffolding for galaxies, while dark energy drives the accelerated expansion of space? Together, they remind us of how much we still have to learn, the mysteries that remain. For every question we have answered, new mysteries arise. The universe is a puzzle with infinite pieces, many of which remain hidden. What lies beyond the observable universe? The observable universe is limited by the speed of light and the age of the cosmos. Beyond its edges, what wonders might exist? Could there be other universes, each with its physical laws and constants? The true nature of dark matter and dark energy. Dark matter holds galaxies together and dark energy drives them apart, yet we do not know what these forces are made of. Could solving their mysteries lead to a deeper understanding of the cosmos? What happens inside a black hole? Black holes are regions of space-time where gravity becomes infinite. What happens at their cores, where the known laws of physics break down? Could black holes hold the key to a unified theory of quantum gravity? The origins of the universe, the Big Bang, marks the beginning of the universe as we know it. But what caused it? Was it the result of a quantum fluctuation, a collision of parallel universes, or something beyond our current understanding? The search for life beyond Earth, the discovery of exoplanets, has revealed that planetary systems are standard, yet the question of extraterrestrial life remains unanswered. Are we alone in the universe? Or is life a common phenomenon, our connection to the cosmos? For all its immensity, the universe is deeply connected to us. We are not separate from the cosmos, but a part of it, made from the same elements that power stars and build galaxies. Stardust in our veins, the carbon in your DNA, the calcium in your bones, and the iron in your blood were all forged in the hearts of stars. When those stars exploded as supernovae, they scattered these elements into space, seeding the next generation of stars and planets. The fragility of life, Earth, our home, is a tiny oasis in the vastness of space. Its fragile atmosphere and ecosystems result from billions of years of cosmic evolution. Did you know that every breath contains atoms that have traveled through the cosmos for billions of years? The drive to explore, humanity's curiosity, is a reflection of the universe's endless possibilities. Every question we ask, every discovery we make, connects us more deeply to the cosmos, an invitation to wonder. The universe is a vast, beautiful, and mysterious place. It is a realm of infinite possibilities where the smallest particles and the largest galaxies are part of the same cosmic story. Let the stories of the cosmos inspire you. Let the stars remind you of the beauty and fragility of life, and let the mysteries of the universe fill you with wonder and curiosity, for in the unknown lies the promise of discovery.